also for a bootstrap. So the bootstrap workshop is happening in 2 weeks of it, but I'll be attending the middle week of it, the week after that. Yeah, you can also drop by. I don't know.
Are the omega the gauge field? Oh, you have the AI on the other side now. Never mind.
Excuse me? I think this is correct.
With what was writing, I thought you were saying the omega were the gauge fields for a second.
No, they correspond. They would descend via C3 reduction, and this is why the reduction of the DC3, right? Star DC3 coupling. Okay, I think we probably want to. No, okay, we should wait for a couple more minutes. So actually, I will also make an experiment. Who has heard of, well, I mean, you all said you had the string theory course, so you all must have heard about the Raman sector, but who knows what a Raman sector is? Okay. So it's a good substantial amount of people because Pierre Raman was sitting right there earlier today, just in case you wanted to know that. No, but I was going to make a joke, but then he said he had to leave in the afternoon.
Yeah, I think he only came for Nadi's.
Lectures, yes, so. Which is fair enough.
All right, well, before Sakura starts.
I was the one who actually mentioned the Raman sector in my lecture, so.
So I made it.
What? I was gonna say, I was going to make the joke, like, here's a Raman sector field, and there's actually an extra copy in the audience, but he's not here. So.
Before we start, I was just gonna, I made a note in Slack, but I was just gonna say in person also that we added an extra lecture next week. So you may have noticed. So Greg Moore is one of our lecturers next week. Greg has been at TASI before. He's always a wonderful speaker. But he's, in addition to his regular lecture series, he's going to give an extra presentation during the Tuesday 3:45 slot, along with Karen Rabe, his partner, another physicist, on the mathematics of square dancing, which he's given this as a talk before, and it just seemed extremely interesting. So this is sort of a bonus thing added to your curriculum. We will not need to dance during the lecture, but we will be watching and listening to some videos while the associated math is described to us. So please join us for that. It was an empty slot that we put it in on Tuesday afternoon. So just if you see that appear in the schedule, you know what happened. So, all right. So we'll turn it over to Sakura for her last lecture.
Thank you. Okay. So I was just putting down what we had discussed last time in terms of the dictionary between these 5-dimensional, strongly coupled supersymmetric conformal field theories and M theories, 11-dimensional supergravity compactified on a Calabi-Yau 3-manifold, which I just denote by X. And I will actually very quickly today focus on one specific Calabi-Yau manifold, and it's a very simple Calabi-Yau manifold, and you'll see sort of why it's useful to have a little bit of geometric sort of training to calculate all these things, but it'll be very concrete. These are really computations that then allow us to evaluate these types of intersection numbers. Anyway, so what was the logic? The logic was, well, we would like to know if you put M theory onto this Calabi-Yau space, what actually is now happening in 5 dimensions? How do I identify properties of that geometry in terms of low energy 5D degrees of freedom? And the first thing is we looked at the C3, 3-form field in 11 dimensions, and decomposed this along 1-1 forms. And I told you that in Calabi-Yaus you have H11 many 1-1 forms. So these are 2 forms that are essentially something like DZ bar. That's how you should think about these. Of course, it's slightly more complicated because it's not just flat space usually. And we saw that these would actually, if you decompose C3 along these two forms, the expansion coefficients are now 5-dimensional gauge fields. They're abelian gauge fields. And if we take the 11-dimensional kinetic term for the C3, which is written there, then in fact, this will give rise to some couplings, Cij, times just this kinetic term for these gauge fields. And this Cij doesn't have to be sort of diagonal. It can have a little bit more structure, and this structure is given in terms of integrating these omega forms, which they're Hodge-star duals, over the full Calabi-Yau. And mathematically, slightly more elegantly, you don't have to write all these integrals and the Hodge-stars. You should really think of the Poincaré dual cycles. So Poincaré dual to this 2 form is a 4 cycle, so S here, Si are 4 cycles, and Cj's are 2 cycles or curves. So mathematically, people would call these here divisors and complex curves, but they're really literally just compact 4 cycles and compact 2 cycles. And then this integral is just saying I intersect this surface with this curve in this Calabi-Yau space. Okay, so far so good. We have a U1 to the H11 abelian gauge theory with this kind of kinetic term. That's not going to be an interesting theory yet. So what I started to talk about last time was that in M theory, you can also, this is M, and this is 5D, you can also wrap M2 branes. So for those of you who are not string theorists, these are 2 + 1 dimensional branes. And we can wrap these on the cycle that are given here. So in fact, we can wrap these on curves to get, and these will correspond to particles in 5D. In fact, we'll wrap them on complex curves, which are calibrated by Kähler forms. In fact, these are supersymmetric particles, BPS states. And we are also saying that the mass of these particles, so given a curve C2, and we wrap an M5 brane on this, is just the volume of this curve. So this is sort of the dictionary mass of this particle, and then also will carry a charge under one of these gauge fields, so AI gauge charge, or U1 to the, we call these here U1I. And so this is the U1I charge. And that's calculated in terms of taking this curve and essentially intersecting with the suitable divisor. This is minus S I dot X with C. And so this is nothing other than integrating omega I11 over C. So that's sort of some very basic things. We'll have particles. Now, if these curves are finite volume, these are massive particles. But now the beautiful observation is actually if we arrange them to be charged so that they have the correct charge to be the W bosons of a non-abelian gauge theory. So if I actually pick Cij, so the Cij is the Cartan matrix of some Lie algebra G, and these Qi's will be charges of W bosons for G. So G will have sitting inside it some U1 to the rank, and the rank here is H11. Then as I take the volume of these curves to 0, I will get a non-abelian gauge symmetry enhancement. So sending volumes of such curves to 0 will actually give us 5-dimensional non-abelian gauge theories. That's sort of the first observation.
Zero after that arrow.
Yes, thank you. Right, so they become massless particles, and if they're charged in the correct way, they will give us precisely the W bosons that fill up the U1 to the rank to a full non-abelian gauge field. So I'm not going to discuss the most general such construction. I would like to actually focus on one specific geometry, and it's extremely simple. So the example is a pure SU2 gauge theory. And I should say one more thing before we go there. And the other piece of the dictionary, which maybe should go somewhere here, I can maybe erase this. Crucially, so the gauge coupling, will be related to, so G is 1 over G squared is the volume of these compact surfaces. So let's focus on rank 1, then there's just one surface, and I don't need to tell you more, but essentially you're taking the volume of this union of surfaces that are in this geometry and that intersect in some particular way to be 1 over G squared. Okay. Yep. That's a very nice question. For this, we will have to go into a little bit more of the geometry, the Kähler geometry, which will take us a little bit out, but I'm happy to discuss it after the lecture. It's a beautiful argument, I think, due to which M theory, F theory is in the title of the paper, but I'll tell you happily later. Okay, so SU2 gauge theory. So this should be a very simple geometry. It's essentially locally, there's one compact. So for those of you who know something about these things, this is just the canonical bundle over F2. If you don't know any of this, it doesn't matter. There's essentially, I will draw you a picture of what this geometry is. So these curves, for most purposes, are essentially compact two spheres. So they are essentially things, they're complex Kähler spaces, so I write them as projective one spaces, but topologically they're just S2s. And in fact, there are two such S2s. One I will call E, and the other one I'll call F. And which one do I want to call E and F? That's important in this picture. This is E, and this should be F. So this is a compact surface, and this surface is called F2, and it's what's called a Hirzebruch surface. So they're actually labeled by positive integers, non-negative integers n, and here this is sort of one of the simplest ones that you can think about. They're always spheres, two spheres fibered over two spheres, and then there's a particular type of bundle, how they're actually fibered over each other, and that's given in terms of this number here, this Chern class. So all we need to know essentially of this geometry is what are its compact surfaces, its compact curves. In fact, there's also a little bit more to this geometry, which is there's one non-compact surface, which is glued along this E curve with another curve, let's call it little n. And here this is non-compact, so the only compact surface here is the surface S. And that in itself makes it only a complex two-dimensional space. And now you need to think of it as there's a non-compact direction that's sort of constructed such that the whole thing actually becomes Calabi-Yau. This is also known, if you're a supergravity person, as the cone over Y2, 2. This is the Sasaki-Einstein manifold. These are 5-dimensional manifolds. And if I put a cone over these, so just ds squared is the r squared plus r squared times this m5, then actually these are Calabi-Yau. They're conical, non-compact Calabi-Yaus. And actually all pure Yang-Mills series in 5D can be constructed from these y, p, comma, q's. I'm happy to discuss this if you're interested in that. Okay, so we are really not interested in too much what exactly this Calabi-Yau is. Really, what's important for this dictionary is what is the relation between the surface and these curves, and how do I actually intersect these things? So I need to tell you a little bit about how one computes these sort of things. And actually, this Hirzebruch surface already tells me the rules about when I take this E and this F curve, and I compute these types of integrals, what they are inside the surface. So in fact, we have sort of, you should think of this as there's an F curve, which is a P1, and that's fibered over an E curve, which is a P1, with a Chern class, which is basically 2. And now, what we also can say is there's an intersection inside S These are the intersections. Now, what do I mean when I say this sort of thing, that E with E is minus 2. So if I have a curve, this is a 2-dimensional, this is in H2 of the surface, then there's a Poincaré dual omega E in H11 of S. And what I'm saying with this sort of, the same is true with F. Because Poincaré duality is now happening in S, and S is a 4-dimensional space. So now what I mean with E intersected with E inside S is just as before. We integrate over E, omega E, etc. Okay? So this is always the rule that these intersections with a subscript, they mean you intersect in that space, and then this should just match up, that you get exactly a formulation in terms of forms if you prefer that kind of formulation. And this is saying in this space this is minus 2, and so on and so forth. Is that sort of clear? At this point, with the time given, this is sort of the very, very crude, but I think this really generalizes to any rank 5D theory. Dictionary, you have surfaces, they're glued in some way, and they have curves inside them, and we can compute from these intersections. Now, we're not really interested in the intersection of E with E inside the surface. We really want to know what is the surface intersected with the curve inside the Calabi-Yau. And for this, we need a little bit more information. Yes, please?
I'm just asking the Hirzebruch surface with the C. That is altogether the cone over the...
This here? Yeah. So the cone is a Calabi-Yau, and this is the y 2,2.
But the Hirzebruch is not
Oh, no. That's a different, so this cone has a different representation, because this is a real cone, right? You have a 5-dimensional Sasaki-Einstein, and you put a real cone over it, something like the r squared plus r squared dm5 squared. This other thing is you have a complex rank 1 bundle over that surface F2. And those two things you can indeed map into each other. In fact, your supervisor was one of the trailblazers in that context, right? So, okay, so we actually want to compute what we want is actually things like S in X with these curves. And that's not the same as just calculating these type of things that you get from these surfaces. And that's again where mathematicians like algebraic geometers like Dave Morrison come in, and they'll tell you how to do these type of things. If you have a curve That's a P1 that sits in a surface, that sits in a Calabi-Yau. Then there's a very nice formula that relates this to that. And I'll just tell you in a second what that is. It's basically saying it's minus 2 minus C dot C in S. That's right. So C, here is E or F, and S is this F4 in that example, right? And now we have, this is more generally true, and it'll be useful if you want to study this in a more general context. If you have a curve C, that's a P1, so it's a two-sphere, holomorphic two-sphere. It sits inside a surface, so this is a complex surface, that's in a Calabi-Yau. Then this number, that's charges and mass, all these things that we'd like to calculate, that's actually computed in this way, right? And it relates the intersection in the Calabi-Yau to the intersection in the surface. So that's basically the utility of this expression. And once we have this, we can now compute what this is for the example we're looking at. So for S is equal to F2, sorry. Right, for this SU2 theory, and we can now compute what are these charges. So this number here was computing the charge under that U1. That's only a rank 1 theory here. So it's basically computing the charge under that U1. So Q under S of this curve E is basically minus S dot E, and that we can now compute the minus 2 minus E squared, or E dot E in S. So this is equal to 0, and QSF is now minus 2 minus 0 is minus 2. So this charge here tells us, and so this is essentially the charge for this M2 brane state that'll have charge minus 2 will be a, sort of the correct charge to be a W boson for an SU2. So it's like essentially the charge of a simple root, but then there's also an M2 bar, and that'll have precisely the 2 charge. And so we get the full, the Cartan plus the 2 roots, alpha. And so if we actually take this A1 from S plus these M2 brane states, they will give rise to an SU2 here. Okay, so this is essentially just evaluating what this compact 4-dimensional cycle does. Now, I drew this additional piece. Okay, maybe I should say one more thing here. So in the limit, when I take the volume now of F to 0, then these W bosons become massless, and we get an SU2 non-abelian gauge group. So the way this will look like is, so F is this curve that's horizontal. So what we're doing is we're slamming this down, and then essentially there's sort of a line, that's all that's left over. And the volume of that curve, the volume of the curve E, is essentially now governing. So it was the full volume of S was 1 over G squared. So in fact, once we take the volume of F, N of E to 0, so, and volume of E to 0, this will correspond to the strong coupling, so the UV fixed point. And then you will see that now this complete surface is collapsed. The curve where E is glued to this non-compact surface is collapsed. And you get something that looks essentially conical. Okay, now there is one other thing which we haven't really discussed, is this N, which is a non-compact surface, a complex, a four-dimensional cycle. So what actually is the purpose of that? Let's think about this non-compact surface as basically a limit of a compact surface. So we said compact surfaces correspond to, right, there are these 1-1 forms, the Poincare dual to the 1-1 forms, so they give us a Abelian gauge fields. They're really gauge fields, and the gauge coupling is given in terms of sort of 1 over g squared is the volume. So if I take the volume of n to infinity, right, so in this, if I put n in here, and the volume is basically going to infinity, this means we're sort of ungauging this. So non-compact surfaces correspond to flavor symmetries. So this actually corresponds to flavor. Right, and so we can repeat essentially the same analysis and get some U1 flavor symmetry out of this. So there's some sort of U1 flavor symmetry. And this is the U1 instanton. So this is basically the U1 instanton that in field theory you would write as star trace F bridge F. But the interesting thing is that it's actually, there's this curve N that attaches to it. And the interesting thing about that curve N is it's essentially the charge under N of this curve little n is -2 minus n squared. And this is actually -2. So from the point of view of this flavor symmetry, this non-compact surface, this actually acts like a flavor W boson. So this is like a flavor W boson for an SU2 flavor symmetry. So what we've learned is in this limit, let me actually continue here because here's this nice picture. If you take the limit where this curve N, which is identified with the curve E of S, if you take that limit where the volume goes to 0, then you don't just get to strong coupling because of that relation there, but you also get a massless flavor W boson. So the limit when G goes to infinity, so when the volume of E, F, and N go to 0, this corresponds to a massless, so in fact you get a flavor symmetry enhancement. From the pure SU, the U1 that you would get just from N to an SU2. And I'm very careful to write here algebra because we'll see in a moment that in fact this geometry will tell us it's not SU2 but actually it's SO3. And that'll be crucial for getting these two group symmetries in this theory. So this theory in the limit where all of these curves are finite volume is a U1 gauge theory with massive W bosons. There's a flavor U1 symmetry. And as we go to strong coupling, so we collapse S and all these curves attached to it, we get a strongly coupled SCFT. One way to maybe argue why it's a CFT is because it's actually a conical geometry. And we get a flavor symmetry enhancement, a non-abelian flavor symmetry enhancement. Okay, are there questions about this geometry, how we computed these things? So in a way, the input you need is these types of surfaces and how they're glued to each other. And once you have that information, you can compute essentially all of these quantities, right? So that's the name of the game. That's why this dictionary is sort of very powerful. You don't need to know anything about these theories too much. You really need to compute this here, and then you can translate it over here. Questions? Yep.
Where to see S-duality or electromagnetic duality from the geometric perspective?
Yeah, so actually, in this particular realization, it's not completely manifest. This theory has a complex structure deformation, which maps it to just F0. F0 is basically just P1 times P1. It's sort of the simplest Hirzebruch. And in that case, you essentially see the S-duality by just exchanging these two. So there's a toric diagram, if you know toric geometry, and then it's just sort of a rotation of this toric diagram. If you know string theory and you know brane webs, you can also think of it as a dual brane web, and that has a rotational symmetry as well. So that's how you see the S-dual of this theory. So here we've kind of made this flavor symmetry manifest, and so it's a little bit more difficult to see in that case. Any other questions? Okay, so now we've got compact curves, compact surfaces. What about how we see, right? So this is now pure SU2 gauge theory. We learned early on in these lectures. Pure gauge theories in any dimensions essentially have center symmetry. And here it seemed like this was an SU2 gauge theory. But one question is, how do we actually extract out symmetries beyond these zero form symmetries? Right? So here there's an interesting zero form symmetry enhancement. What about these higher form symmetries? Or put differently, what about extended operators? For example, line operators. Okay. Who has a guess what that would be? So these are world lines of infinitely massive particles. How would we realize them in such a geometry? So particles of finite mass are given in terms of M2 branes wrapping curves of finite volume. Right? That was the. So if I want to now look at a line operator, I need to wrap it on an infinitely extended curve. So there will be. So this is now when it's important that these are actually non-compact Calabi-Yau. So a Wilson line, right? If you think of it as a world line of an infinitely massive particle, then we are now, so we should then wrap M2s on non-compact curves, or two cycles. Yeah, so if you have this geometry, so one way of thinking about this geometry is it's conical, it has this sort of 5-dimensional boundary, and so we have curves that are compact. So these were these little P1s, so these are compact curves C. And now what we actually want to study is something like things that extend out to the boundary. So this is a non-compact. So they're basically given in terms of something that ends on the boundary. So mathematically, these are characterized in terms of so-called, they're not just two cycles, but actually you need to also specify that they end on the boundary. So this is the boundary, this is 5-dimensional space. So these are non-compact curves in this Calabi-Yau. They're called relative two cycles. So is that actually, should this group already be the full one-form symmetry, or the sort of the distinct line operators? Not quite, because indeed it could be that these lines could end on compact 2 cycles. Right? So it could be that this sort of ends on a 2-sphere that's compact. So in fact, that's precisely the screening picture. I can wrap an M2 brane on this, and actually if it ends on a compact cycle that's not sitting on the boundary, then actually it becomes trivial. So the actual sort of one-form symmetry group will be related to a quotient. So this is the line operators modulo screening will be H2 x dx z modulo the actual compact 2 cycles. Right? So these are the non-compact, and these are the compact. So these would give rise to actual local operators, and this is sort of the line operators when you wrap M2 branes on them. And so in fact, this here is precisely, everything is abelian here. These cohomology groups are all abelian. So in fact, this is precisely the dual, Pontryagin dual of the one-form symmetry group that's isomorphic to the one-form symmetry of that of the theory that you actually realize with this Calabi-Yau. Cool. So then it's a matter of calculating now how do you compute this thing? And again, that's sort of where we need to go back into this Calabi-Yau geometry, but it's always hidden inside these intersection numbers. And in fact, the way to sort of compute this is the following sort of nice little observation, that this quotient, so G1, can be computed from intersection of compact 2 cycles, 2 and 4 cycles. So essentially, these charges that we already calculated. So actually add a little bit of more detail here because it might be useful to even understand how this group sits inside this group, which may not be completely obvious. So if in this relative cohomology, there's a long exact sequence of cohomology groups, which essentially, I'll just explain every sort of step in it. It's all very intuitive. So this goes on forever and ever, right? And so what is this sequence? It means, again, at every slot, it's an exact sequence. So the image of this is in the kernel of that. Now, this here is just saying I can embed compact cycles into this relative homology group. It just means that the part on the boundary is trivial. Now, what this here means is the ones that are relative homology group elements that don't come from compact cycles basically have to have sort of support on the boundary. Right? This is a purely boundary homology group. And so this, of course, then extends, and you can do this for, for all the i's, and the degree here has changed, right, from I to I minus 1. And the way to think about this is there's a cycle, and it ends, so there's a 2 cycle, right? And the end of it, this is now contained in the boundary of X. Right? So this is this blue cycle. It goes all the way to the boundary, and on the boundary, it now really has some non-trivial homology class that it ends in. If it didn't come from something that was just located in the bulk. Okay? So this is how you sort of think about this long exact sequence. Now the question is, what we're trying to calculate is essentially sort of the quotient hi of x del x over this image of hi of x. So that naturally, in fact, sits also inside I minus 1 of the boundary, so in h1 of the boundary. So this is then the statement. So this one form symmetry sits actually, in fact, inside the h1, and it's equal to that if, oh, I got this wrong, if all one cycles extend trivially to x cycles in del x, right? If there's nothing that the one cycle actually extends into, so there are no one cycles in our Calabi-Yau. And for most purposes, Calabi-Yaus don't have actually one cycles, unless you do something drastic to them. So in fact, this is actually true. This is equal to that. So one way you can calculate the one-form symmetry, if you like Sasaki-Einstein spaces, you just calculate the first homology of the Sasaki-Einstein space. Right? So if your x, this is for the people with Sasaki-Einstein or holography background, if you're YPQ, then you can compute the one-form symmetry of this thing, of this x, is just h1 of this YPQ, comma z. And it's very nice because this is all toric, so there's a very nice combinatorial formula. And if you do this exercise, you'll find it's actually z p comma q GCD. This is GCD. And let me add one more comment. These are realizing actually the SUP with theta and q theory. So there's an instanton particle of charge q, and that can screen part of the one-form symmetry ZP, and that's why it's a GCD. But we're really interested in 2,2, and in 2,2 this gives precisely Z2. That's sort of one way of computing this. I actually want to go back, and this is just a side comment if you're familiar with these spaces. There's actually a nice intersection way of computing it too, which will become useful when we're looking at the two-group symmetry in a moment. So, okay. So I want to label these maps HI, no, H. Yep.
Is there a symmetry between P and Q in the
Yes.
How do you see that in terms of instant outside this?
You don't see, there's not like a symmetry in terms of the theories. It's just that in one case you have a ZP, one-form symmetry, and you put an instanton particle charge Q in there. In the other case, you have a ZQ, and you put an instanton particle charge P in there. Right? And so it just reduces it to the same group. The toric diagrams are quite different. Right? SUP Q1, so these are like these sort of things, and then you can raise and lower these sides, right? Those are the toric diagrams. So I just want to label these maps. So this actually is GI, FI, and H, and minus 1. So in fact, what we're computing is the kernel of H1 or the image of G2. Yeah, so this one-form symmetry group here is in that language over there is the same as the image which is the same by this exactness of the kernel of H1. Okay, so from the intersection numbers, we can also determine these maps. And in fact, this map F has a very simple interpretation. So this map F2 from H2 of X to H. So this actually, this map over there is precisely the map HI into HI X at H2 X del X. This is F2. This is given in terms of, so here we have some Betty number B2 rank, and here's a lattice with B6, because this here is basically isomorphic to H6, H4 of X dot XC for non-compact. So in fact, what I'm trying to say here is, although this looks like you have to think about the two cycles and then the relative two cycles, in fact, the rank of this is given just in terms of the Poincare dual of it, which is actually H4 of X del X, which has B4 rank. And this matrix here is just the intersection matrix again. Of the compact surfaces with the compact curves inside some matrix Mij. And now you go from this lattice to that lattice with this matrix, and I just need to compute essentially what the what basically comes into the image of this map. So the one-form symmetry, if I write in this way, is given in terms of the lattice B2 modulo this matrix times Z B4. And this matrix is essentially computed before in, okay, it's gone, but when we were doing these computations here, so that was given in terms of just, in our example, one was charge -2, the other one was charge 0. This was F, this was E, this was S. So if we take this quotient, I get also Z2. Check. Yeah. So either you know what the 5-manifold is and you compute the first homology, or you know the intersections of curves, compact curves and compact surfaces, and then you compute essentially this quotient here of this one lattice over the other. Cool. So that explains how from the non-compact curves in the geometry we get line operators. When we take into account screening, we get the one-form symmetry, and indeed this seems to be consistent with the picture that this actually is engineering an SU2 gauge theory. Right. So we have about half an hour, so I can now go over it. So are there questions about this? Yep. Yep.
What part of the story have to be modified?
Yeah. Okay, great question. So indeed, what I actually skipped this, but I will actually tell you the more general story, how we get an arbitrary, because now in 5 dimensions, you can have 0, 1, 2, 3, 4 form symmetries. So how do they actually come about, and how do the dual symmetries come about? Actually, I'm telling you about the charged objects rather than the symmetry generators. And if you want, you can ask the question, how do you see the symmetry generators, and we can discuss that also. Okay, so we can also, of course, as Sal was just asking, we can wrap not just M2, but also M5. And really, here we looked at the second relative homology quotient, but we could wrap them on something that I'll call HK, which is sort of the kx del x. So these are relative. So one way of saying it is these are non-compact k cycles modulo compact k cycles. So these are these relative k cycles. For k equals to 2, it's exactly what we calculated there. And now if I actually take the q, so this is the GQ. So Q equals to -1, Q equals to 0, Q equals to 1. And I take here K basically to go through. So I get an electric one-form symmetry from H2. So this is G1 from H2. And so here I'm wrapping M2 branes, and here I'm wrapping M5 branes. There's some table that I'm trying to write down here. Now, I can also wrap, of course, M5 branes on these. And dimensionally, what I'll get is these are going to give rise to down here, Q equals to 4. So Q equals to 4 is down here, and it gives you from the M5 branes on H2. So if you take a 6-dimensional object and you wrap it on a relative 2 cycle, you get a 4-form symmetry. I will move it in a second. This is not really that interesting. What you were asking is, how do I get the dual 2-form symmetry to the 1-form symmetry? So in fact, for this, I have to actually wrap M5 branes on the dual cycle. So this actually gives me relative 4 cycles. So I take an M5 brane on a relative 4 cycle, so non-compact 4 cycle, modulo screening, and that'll give precisely generators of a 2-form symmetry. So these are sort of the, right, and these are basically paired. You're dualizing the brane and you're dualizing the cycle, the 2 cycle to 4 cycle. Okay, and I'm just going to fill up this table. So for the 0, minus 1-form symmetry, you have H4, H3, H1, and H0. And over here, you start slightly later, and you get to H6, H5, 4, 3. So this is saying if you wrap an M2 on these relative cycles, you'll get these types of symmetries, and M5 on these types of relative cycles, you get these types of symmetries. And if you are now asking, what exactly indicates in a string theory context which polarization you've picked, 1-form symmetry versus 2-form symmetry, that's actually an asymptotic flux configuration that fixes, do I now actually look at the electric objects, the M2 branes, or do I look at the M5 branes? So that's actually an additional datum I need to supply with some additional fluxes on this color wheel. Okay, and often sort of the sum of these things is called the defect group of the compactification. And that's sort of not yet choosing a polarization in it. Okay, any other questions before we head to the 2 groups? So one interesting point is this 1-form symmetry we calculated on the Coulomb branch, right, in this smooth geometry. But of course, as we go to the singular limit and collapse all these curves in the surface, that still stays. Yep?
I guess the obvious question is, what is the minus
So minus one form symmetry. Think of it similar to like a theta angle. It's a parameter of your theory. Essentially, yes. There was another question.
Yes, you might have already said this, but do I have to be careful what kind of cycles I'm
Yeah, so, okay, you're asking about supersymmetry. Right. So I think everything we've talked about is in this sort of supersymmetric context. We're wrapping branes on holomorphic cycles. So they're actually supersymmetric objects. But in principle, you should also be able to extend this to the non-BPS part of the theory, but that's extremely difficult. Okay. So now we're putting two complicated things together, two groups, and geometric engineering. But so in this case, right, what I just said, the one form symmetry seems to be there or also on the Coulomb branch. This two-group symmetry is really tied to taking the limit of the SCFT. So this is something that really exists at the UV fixed point. When you go away from it, you destroy the symmetry. So the two-group we already have a good starting point. There seems to be a non-abelian gauge symmetry flavor symmetry enhancement as we go to the SCFT. But one of the important points was you only get a two-group if this flavor symmetry group is not simply connected. So it should not be SU2, but actually it should be SO3. And to determine all of these, so the key ingredient in this two-group was this curly E. So this extension kind of group, let me remind you, this was sort of, we had a one-form symmetry, and it projects to C. And this was part of the flavor center, and this is part of the center. What we'd like to do is compute essentially these charges of local operators, but now keeping track of their flavor charge. Remember, this was this picture. We screen now line operators by keeping track also of the flavor symmetry charges. So to determine charges both on the gauge and flavor. We already said this curve here, this E curve, basically this N, which is identified with E, it is essentially the flavor W boson, but it means also that this curve E has a potential of now being charged under both gauge and flavor symmetry. Actually, it's the F curve that's charged on the flavor and gauge symmetry. So both of these curves, now we need to compute their intersection with S and with N. So the game here is really, you have curves, you have surfaces, you calculate how they intersect with everything that you have in your geometry. So this is Q gauge, so this is QS. So this is minus S dot C, and then there's Q flavor, and this is minus N dot C. And these numbers are basically things we computed before. Actually, maybe we want this, and we do this. It doesn't, the overall sign doesn't matter. And you see there's indeed a curve that is charged under both of these symmetries. And if we actually just look at the flavor center symmetry, which is a Z2, so we reduce this mod 2, this charge, then this is just 0 mod 2, and this is 1 mod 2. So in fact, we see that we have essentially this non-trivial Z2 sitting inside there. So this intersection matrix will tell us what happens, whether there's actually a non-trivial two-group symmetry or not. Okay. So this let's call this matrix here N. So this is just the 0, 2, 2, minus 1. And we should think of it as the matrix of gauge and flavor charges. And now the point is this curly E group can be calculated as the lattice Z2 modulo this N times Z2. Right, so if we restrict to the gauge charge piece, this is the computation we did over there. And it computes the one-form symmetry. If we just do this here, we compute the flavor center symmetry, and that's Z2. And so if we combine this, then we also get information about how the particle, now there's a single particle charge under both of these, and they'll account for these things. And if actually this is just a diagonal matrix, they will not, or if it's equivalent to a diagonal matrix, you will not get any two group. So this actually is useful to compute this quotient essentially by taking, this is isomorphic, to taking what's called the Smith normal form of this matrix. So if you do computations for higher form symmetries in geometric engineering, you will start appreciating the code in Mathematica, the command Smith decomposition, and that's computing the Smith normal form. And what this essentially does for you is it writes down so matrices A and B, they are both integral matrices that transform this matrix into a diagonal matrix. So there's sort of N, which is now M, and in this case, M is just 1, 0, 0, 4. So this indicates that this quotient here, this E, is in fact in our case Z mod 4. So that's good. So Z mod 4 is this curly E, and that was also, and we know the one-form symmetry is Z2, so the projection is C is Z2, when G1 is Z2, and so C is Z2, and in fact, this will tell us the flavor symmetry group is SO3 rather than just SU2. So if I go to the strong coupling, I collapse this curve, I collapse the surface, then in fact this is not an SU2 but an SO3 flavor symmetry group. And actually there are nice checks of this statement also using localization results, using the superconformal index. You can check that you actually get SO3 representations in this superconformal index computation under the flavor symmetry. This also gives you a way to compute the flavor symmetry groups even if you don't have one-form symmetry, right? So this is another nice exercise to do. Okay. So what we found is as we take, actually this is a good place. To argue for this. So if all the volumes for F, volume of E, and it's also the volume of the full surface S are finite, you just get a U1 Young-Mills theory, gauge theory, with some matter that is charged as coming from these W bosons. If we take the volume of this curve F to 0, we get an SU2, this is our gauge group, and a U1 flavor symmetry. So there's also here this U1 flavor symmetry, this is instanton symmetry. But this is sort of still, because this curve here has finite volume, you still have a U1 flavor symmetry. So this is our flavor. But as you go to strong coupling, now we take volume F and E to 0. So this is the SCFT. We get an SO3 flavor. which forms with the Z2 one-form symmetry a non-trivial 2 group. And one way to also, of course, make sure that there is a non-trivial 2 group is to say that this flavor symmetry will have a non-trivial W2, which will then precisely with this with the one-form symmetry form this Box-Stang type 2 group. And it's absolutely crucial that we have this SO3. On the Coulomb branch, as when we have sort of finite volume for this curve E, so we're still at recoupling, you have also a one-form symmetry, but this flavor symmetry, in fact, does not allow for a 2 group. And one way to argue for that is to say, well, this is a side comment. If you look at, so this W2 is in H2 of B of the flavor symmetry group, so BSO3 with Z2 coefficients, so this is C. This is non-trivial, and so we get a 2 group like we discussed in the last lecture. So there's a Box-Stang type 2 group. However, on the Coulomb branch, so at recoupling, this BU1, so that a flavor symmetry group is BU1, does not. So here's some A1, there's some pullback. Where A1 is a map from BSO3 to our space-time. We're pulling this back, sorry, this way around, and into the SO. Anyway, so BU1 does not admit such a W2 class with Z2 coefficients. So there's no 2 group. Okay, and so it was absolutely crucial to be able to compute these charges to determine the symmetries. This computation is done in this sort of frame where these are still at finite volume, but then it also tells us that at strong coupling, you actually do get the symmetry enhancement. So probably the better way of saying it is, as you are at this fixed point, you have collapsed all these cycles, here's the SCFT, you have a 2-group symmetry from the SO3 flavor with the one-form symmetry, and then if you do some relevant deformation, which in this case is the gauge coupling, you break these symmetries. Okay? Yep. Essentially, you still have these charges, but you don't have this class. With BU1, with Z2 coefficients, this is 0. That's the issue. So that's also another nice demonstration. This is a necessary condition for 2 group that this does not split, but it's not sufficient. Right? You really need to be able to also have then a non-trivial class such that you can get a really non-trivial delta B2 out of it. And so this is really a strong coupling phenomenon that you see here. Okay, so let me perhaps summarize a little bit what the whole point of this sort of geometric engineering of these CFTs is, and also how far one can go with this. What we actually mapped out is how these geometries, or some kind of information that's encoded in these geometries, how that's sort of translated into field theory data, and it allows us to actually go to strong coupling, really to infinite coupling, and that's where the CFT sits. There are many other examples like this, and let me just sort of give you an overview of what sort of setups can be studied with this sort of technology. Right, so you can take, so in 5 dimensions, so these SCFTs, they have always n equals to 1 supersymmetry, which means 8 supercharges. And they come from M theory. on a Calabi-Yau 3, but it needs to be a Calabi-Yau 3 that has singularities. So it's absolutely crucial that there was, in the end, when you collapse this becomes a singular space, and then you can smooth it again, and you get to smooth Calabi-Yau. So these are singular, so-called canonical canonical singularities. So canonical here means they admit some sort of Calabi-Yau smoothing. Which is preferable because it gives you then still a supersymmetric theory. In 6 dimensions, if you start with 2, 0 supersymmetry, you can realize all of these. And the claim is if you have a classification of such non-compact Calabi-Yau 3, you potentially have a classification of 5D SCFT. So that would be a very powerful thing to be able to actually state eventually. So at the moment, there are many, many examples, and there are some claims, but I don't think there's a full classification, neither mathematically nor in the CFT literature. 62, 0 is classified essentially by ADE gauge algebras. So this is type 2b on Calabi-Yau two-folds, which are of the type C2 mod gamma ADE, where these ADEs are finite subgroups of SU2. And in this case, again, we can very quickly determine, so the way you should think about these is these are cones over the boundary of C2 is a 3-sphere, and now you quotient by this finite group. So you really, the boundary of this is an S3 mod A gamma ADE. So these are again cones over now 3-dimensional spaces, sphere quotients. Just a sort of very quick eyeballing of what sort of the geometry of these is. Essentially, when you smooth these, you get these P1s intersecting in some Dynkin diagrams. So Dynkin of ADE type. And now we learned, well, we can take now the suitable Ramond-Ramond field and reduce this along these. There'll be a similar story to what we did for the M-theory case. And so these actually should give rise to some sort of gauge field, but actually these are tensor multiplets, and this is sort of in a smooth regime where these theories, this is the tensor branch, of the 6D theory. And we can also very sort of quickly compute what is the two-form symmetry or the defect group of these, which is just given in terms of H1 of these spaces, or the organization of H1. So here there's some kind of, it's not really a two-form symmetry group. So we put this in quotes because it actually does not really an absolute theory associated to this, but these are actually given in terms of the abelianization of this gamma ADE. So this is really the defect group. And the charged objects under these are strings. And they come from the 3 branes wrapping on these P1s. So in fact, we can realize these geometrically also. And they're already classified in terms of sort of ADE gauge algebras. The interesting case occurs when we study 6D, like minimally supersymmetric CFTs. So all of these are strongly coupled theories, right? Just to emphasize this again, both these and these. And then the sort of last class is 61,0 SCFTs. And these are modifications of this. These are basically what's called an F theory on specific Calabi-Yau3. There are again singular Calabi-Yau3 that have admit with a T2 vibration. So this is a non-perturbative version of type 2B string theory, and essentially by admitting this additional T2 vibration that varies the axodilaton, you actually generalize the setup here. And again, we can, here there's now a sort of a classification or claim classification. Geometric one, and here of course too. So you can study all of these strongly coupled CFTs using these geometric methods, and now we also know how to compute all these, some more refined information about their symmetries. It doesn't stop with these higher dimensional fixed points. Of course, they are very closely related four-dimensional SCFTs, in particular with n equals to 2 supersymmetry. And they arise from type 2B, for example, on Calabi-Yau3. So very much these geometries we studied here in 5D, we can compute also the reductions on these Calabi-Yau3s. And these are usually, very often, these are non-Lagrangian theories. So for example, if you know a Juris-Douglas series, they are precisely of this type. So it gives you sort of a sense of this is not just sort of curiosity, but it gives you a very powerful sort of way of studying theories that with perturbative methods you may struggle to actually get any kind of handle on. Like you don't have a Lagrangian, the fixed points, it's an infinite coupling, then string theory is your friend. Okay? So I will finish here. Are there any questions about computational things or the general setup, whatever I've talked about? Also the first part that was more generalized symmetries that maybe more people connect to. Yep.
You were saying about its classification of 5D SFTs using the solution of symmetry. Like there might be other like this. So
yeah.
How many data do you really need to characterize?
So I don't think you can just classify them using these geometric information, but they do help, tell you a little bit more about what happens at the fixed point. Right? It's sort of surprising that you get this, at the fixed point you see this two-group symmetry. But the classification, the reason why it sort of is a little bit, I think, not completely resolved in this Calabi-Yau setting, because although mathematically, canonical singularities are extremely well understood, as a physicist, you really would like to not just know they exist, but you want to calculate things like intersection numbers. And that's something where you then need to start resolving these Calabi-Yaus. And that's then a much more, complicated task than just saying there's an existence proof. Yep. Sorry? Oh, okay, so then you just take M5 branes. It's a single tensor multiplet. I think that's the one you know best, right? So a single tensor multiplet, we know everything about it. We can reduce it on a curve, on a 3-manifold, 4-manifold. Yeah.
All right, well, let's thank Sakura for her whole series.
The tone actually is already in that singular limit, right? Yeah. Cross section.